morning and good afternoon. My name is PhD student of the University of Messina. And the work I'm going to present today deals with the finite element analysis of cruciform welded joints. And this was made by considering different mechanical properties of the base material, heat affected zone, and weld metal. The outlines of the work are the following. First, I'm going to talk about the materials and the methods that we used. Then I'm going to describe the hardness measurements performed in order to identify the local properties which were related to the stress-strain curves for the different material zones. Then I'm going to describe the experimental tests which we performed and which we used the DIC technique in order to detect the local strain and displacements. Then I'm going to describe a nonlinear finite element analysis, and obviously this will be compared to the experimental test, and at the end we have the conclusion. The material used is a mild steel, widely used in the naval field, and the welding technique was a full penetration welding using the MIG process. In these figures we see the real welded joint and the nominal geometry of the welded joint that we used for the experimental test. The hardness measurements were performed with an innovative method, which is called the UCI method, which consists in, is based on the natural resonant frequency of a bar, which is excited, and push the Vickers diamond into the sample. This is obviously, this frequency changes, and these changes are related to the hardness values of the sample. The accuracy of the instrumentation is about 0.01 millimeter, and we are able to have a whole map of the hardness measurements. Here we see the test. We see the polished specimen, and we can also see already here the different material zones. On the other figures, we see the hardness measurements, a whole map of the hardness measurements. And on the right figure, which is this one, we see that we ordered the hardness values in groups. Using these groups, we related the hardness values to the ultimate and the yielding stress of the material. These two equations were taken from literature, from a recent paper of Lopez and Fatemi. And using these equations, we define the different material characteristics that we are going to use. So, just resuming, first of all, we define the different groups of hardness values. Then HB values were first converted in HB hardness, and sigma, the properties, the stress-strain curve was evaluated, and the elastic strain was simply calculated as the sigma E ratio, while the plastic part of the curve was calculated using the Ramberg-Osgood equation. And also the Luder's plateau band were kept, and obviously the base material curve was validated with the hardness measurements. After this phase, we proceeded with the experimental setup, in which we see in this figure. We also see the DIC measurements, which is provided from the dome. And in this figure, we see the input parameters, which this test is a displacement control test, And this is the force revealed by the load cell from the machine. And instead here we see the deformed specimen at the minimum load. It's possible to observe that symmetric displacement values arises, but at the same time we observe different values of maximum and minimum load. And moreover, the minimum load is not in correspondence of the minimum displacement. This means that the specimen deforms in a way the bending arises, causing a diminution of the load. And it's also possible to see from these figures at the minimum load. The DIC analysis performed, we analyzed max load and min load. At the maximum load was observed that there is a difference in terms of strain along the X direction, which is the vertical direction, from one side to another. At the maximum load, this effect is even increased. In fact, we can see that are present negative and positive strains. And also, during these measurements was observed that large strain occurs close to the notch, but they become even larger along the base material. After this test, we performed a nonlinear finite element analysis using the ANSYS software, and we developed a 3D model, and which uses the solid 186 type element, which has 20 nodes. And this is the size of the minimum size of the element at the notch of the specimen. The nominal notch radius is 1 millimeter. The strain curves used were the one that we defined before from the hardness measurements that I was discussing before. A preliminary analysis was performed. First, in the elastic phase was observed that the strain in the vertical direction is higher close to the notch. While in the elastic plastic phase, so for a nominal stress greater than the yielding stress, we see that the strain in the X direction evaluated in the notch is higher than in the elastic phase. But we observe that it's smaller near the notch with respect to the base material. And this effect is due to the differences induced by the hardness values to the material characteristics. Because as we saw before, the welds are much higher than the base material. Obviously, a comparison between the two techniques was made, and here we see the deformed shape of the specimen at the experimental test, and here we see the deformed shape of the finite element model. The finite element model also captures the bending strain for F max and F min. And the strains has happened for the DIC measurements are larger along the base material than in the weld metal. This means that behavior is well represented, but the values in terms of strain along the X direction still differ from the experimental data. This is probably due to the residual stresses. For this reason, another comparison was made. This was made in order to avoid the residual stresses, and so comparison was made between F max and F min. As we see from this comparison, there is a general good agreement, even if there is still some difference, which because the finite element model exhibits larger strains in the notch proximity with respect to the DIC measurements. So we can conclude that we were able to develop a procedure in order to investigate the cruciform welded joint. We were able to define different material zones from the hardness measurements with this innovative technique that we used. We performed also a nonlinear finite element analysis, considering these different mechanical properties. And the finite element model was validated by means of the experimental test that we performed with the DIC measurements. Obviously, there are still some differences, so the model needs to be improved. And these differences could be reduced by taking into account a major number of hardness levels in the finite element model. Thank you.